So I'm aware that we are in a room of a lot of atmospheric scientists. Now we talk about brain dynamics, and I think there are 2 or 3 arguments why this might be relevant for you as well. First of all, today there's a lot of hype about deep learning and neural networks and things like this. So I'm talking a little bit about this in a generalized sense. Neural field theories are continuous versions of neural networks, and we talk about learning in our third part. Second, we all do state estimation in data assimilation usually, and we have heard already in the first talk by Geir Evensen that inverse problems or parameter estimations and state estimation are very, very, very close to each other, and they should really be kind of considered as 2 parts of one bigger problem. And so here, the question I asked myself, and this is joint work, by the way, I should have said this in the first page, with a PhD student, Jehan Alsweili from the University of Reading, and she will present this also in a poster on Wednesday. So, So we do the state estimation in data assimilation and also an inverse problem. And here we asked ourselves, how do we couple these 2 problems together in an appropriate way? And I'll explain this in a second. So I will show you some introduction, the state estimation, the neural kernel or learning problem, and then how to integrate them into an iterative procedure and how to solve them and make some remarks on convergence. So in neuroscience, basically one of the basic problems of neuroscience is you have all the connectivity in the brain or in other type of tissue, and you want to reconstruct the connectivity from measurements. And it's a big problem, millennium problem, not really solved for practical systems usually. So here we are looking into some simple versions of this and try to see what we can do. So neural activity in some part of our brain, and then we measure some function of this neural activity either at some points, so P, J is 1 to M measurements here, or we put electrodes somewhere and we measure some integrated version of the neural activity. And there are basic tasks here: estimate the neural state given the measurements, and second, reconstruct the neural dynamics by reconstructing the neural kernel, and then how can you combine the 2? So one very old, 50 years old, way to model neural activity in a continuous version is the Amari or Cohen-Wilson equation. It's an integral differential equation. The change of U is a measure of the neural activity. It can be a potential. It can be just a statistical measure of the activity. Is given by minus U itself. So this is a kind of going down, and then there's an excitation term here. So U at a point Y will in a nonlinear way excite U in the point X here, and you have the connectivity from Y to X given by this kernel W here. So this tells you U will change, it will go down if nothing happens, and if you have an excitation, it will go up in time, excited from all the other parts of the space or the brain with this connectivity version. And you have some initial condition, and then you integrate this equation, and that's basically your neural field model. And it's basically the same in each neural network with different designs, of course, but that's the basic game. So how do you solve the forward problem? Just one slide on this quickly. In principle, you integrate this with respect to time. So if you integrate this with respect to time, you get the U out here, some U0, and here you get an integral of this right-hand side together. And we summarize this as A here on this slide. And you end up with a fixed point equation. And if you want to solve fixed point equations, usually you use Banach fixed point theorem. If you could show that this is a contraction, it would apply immediately. You would get unique solvability and a couple of methods. And indeed, if the F is differentiable with some bounded derivative, then it's a contraction, and then basically you can apply Banach fixed point theorem, and the whole theory for the forward problem works fine. So you can integrate this and will always be stable and bounded. And we come back to this on my last slide. Yeah, we need this. So I take one example here for you. It's a simple oscillator here, this is my model, and so basically this is what I want to put in and want to use and want to measure and want to train the network with. And it's kind of also relevant to the atmospheric sciences because we have oscillators in our atmosphere everywhere. And if we could learn this, it could be part of bigger systems. So and if you ask yourself what type of neural kernel would lead to these oscillations, you look at this image here. We come back to the others later. And this basically tells us you have 3 blobs here in this point. So the kernel connects here. Each point on this, my brain here is just a circle, yeah? So I have neurons on the circle, and they have some activity, and they oscillate with their activity over time. And the kernel will connect each neuron with each other. So here it's nice to plot. This is why I chose the example. And in the kernel, it's just a 2D kernel. And if you have the 3 blobs, it's this neuron will excite this one will excite this one will excite this one, and it goes all the way around in the dynamics. So just an easy example. And the red one will be the learned one later. So let's look at the state estimation for 3 minutes. So there might be different types of measurements usually. If you go to neuroscience, what people do in medicine, either they have very tiny electrodes and they put them on the brain, and then they have this type of point measurements here. This is a pulse in 2D now, something like an excitation. Or they put electrodes in which are larger and integrate some area. And then if you would put a lot of electrodes on, you would get this type of signal, all of them integrated as a forward operator here. And then again, some signal here. I have another example here. So you can write it as a classical data assimilation problem. So this is known to all of you. H is now my observation operator. Either it's a projection or it's an integrated type of observation operator like we have in the satellite, for satellite data. F is my measurement. R is my error, covariance error. B is my background covariance. And here phi I call some kind of initial state or first guess, and then phi is the minimizer. I minimize over phi here. You all know this type of update formula. It's called Tikhonov regularization in one community. It's called kind of 3D var or 4D var if you do this over time as well in the other community. And you could write it in different forms like this. As we had all this already in the first talk. And the star is for the adjoint here in a proper scalar product. If I use the scalar product with the B and the R, this is what I get actually. And so you can just use this as a state estimator by minimizing this problem. If it's linear, you get this type of thing. So, so you can do this, and you need a covariance matrix. And for the brain, you usually don't have this, and you can't measure it in detail. So you might just use a Gaussian covariance matrix. Here it would be for 1,000 or 900 points in each direction. And here you see different points, the covariance to the neighborhoods. And so Gaussian covariance matrix. If you have this electrode case, it's an ill-post problem, so you get singular values going down exponentially. This would be similar to YASI or other kind of satellite data. Quite similar behavior. Okay, so here just an example. If you do the state estimate for these 3 situations, different pulses, here measurements, point measurements, and here, basically, I just use 2 different regularization parameters, one very small and one a little larger. And so you get basically a blob back here, not exactly the one, depending a little bit on the distribution with these few data points here. But in principle, you get some kind of a smoothened estimate of your result out of this. So that's the state estimator. Let's look into the learning problem, the second part here. So here's my Amari equation again. And now I assume that we know the U over time. So for all times and all points in space, I have calculated the U. And now I want to learn the kernel. And how do I do this? Here are my 2 examples. Here's a pulse going through. Here's my oscillator. You can do the following. First, you summarize all the terms outside of the integral into one variable psi here. And you summarize the term f of u, which is also known. I assume f to be known here. Usually it's a sigmoidal function going from between 0 and 1 in a nonlinear way. So this is known, and then this is the integral operator where I don't know the kernel W here. And this is to be calculated. And you can basically write it like this. So the psi and the phi would be known, the W is unknown, or it can be written, if you look at this equation, it's for all x and all t, this integral. If you keep x fixed and just let t run, then it boils down to this integral equation of the first kind. So this is your kernel now. W of x is the unknown, and this right-hand side or left-hand side is known. So you can basically solve a family of integral equations to solve the learning problem here. And you know, usually this is an ill-post equation. It has to be stabilized to properly work, and basically use a technique which is exactly, again, something like 3D var or Tikhonov, and we can just do this and any other one. So if we would use now A for this operator here, we basically solve this in a regularized way by Tikhonov with regularization parameter, and so the pulse kernel reconstruction can be approximated by solving a family of integral equations. I show you some result here where this has been done for a delayed version of the Amari equation recently by Jehan. So this is the input signal here over time, these different oscillations going up and down, noise on the input signal, and here different kernel reconstructions, where here this is with a low regularization parameter, and here with strong regularization where you get basically a relatively good approximation. And here you see the error in 2D of the kernel with noise. And if you then integrate this kernel, you basically get this curve back, if you use a very good signal as input. So now let's come to the more realistic point. You measure over time at different electrodes or different points, and now you have nothing given, and how can you reconstruct this? And of course there is a easy or naive approach which you can try, which is estimate the states from given measurements first, and then reconstruct the neural kernel after you have done this for all time steps and all points in space. Yeah, so first you go from your measurements to your states, and if you have all the states over time, you determine your dynamics and solve the inverse or parameter estimation problem. And of course, if you do this, if you have no knowledge of anything at the beginning, it's very tough to get a very good estimate of the states. So an idea coming from these two steps immediately would be, why can't you just do the estimate of the states and get your estimate for your kernels, and then go back to the first part, estimate the states again. Now with the kernel you reconstruct it, and then you iterate the whole thing and what will happen over time. So I use this data assimilation and inversion power n here because you just iterate it. And here's basically just an idea to show you what happens for the pulse case, and I show traces. So this is all times summed up. 3 slides left. So some measurements here, the electrode case and estimate, and here the reconstruction after the kernel estimate. Here I show you what happens now. I have just some remarks on this. So here I do the transport map. Given a kernel, I calculate the states. Given the states, I do the estimator from the data, and then now I have an analysis state. I can do the estimator W for the kernel again. And then I basically go around here, and we looked into the mathematical theory of this convergence and stability, and this is just a summary slide for this before I show you this final slide. The transport map is bounded, as I showed you, coming from Banach. The estimator is convergent if you have enough data, and if you have the true data, you can choose all your parameters in a way that you get the kernel estimated. And the reconstruction is convergent and bounded as well. So altogether, the iteration is convergent in the sense that if you had enough measurements, it would just go over time, go to the correct solution. Of course, if you don't have enough measurements, if you have null spaces, etc., you have to take care of this. And for noisy data, you need a stopping rule at some point, otherwise you get worse and worse again over time, which is well known as a phenomenon for iterative methods for inverse problems. And here I have just shown you the iterations for the iteration 1, 2, 3, and 4 over time, just to remark, if you just do this in a naive way, you see here, this gives you something, but it's too slow, the red one. It's lagging behind. It's just going one circle and repeating it all the time. But if you go several iterations, you end up with something which is now getting the right speed of the oscillator. This is the reconstructed full dynamics, and this was given with no knowledge of anything. Okay. You can also see this here. If you look at the iterations, you get it wrong in the first step. This tiny gray ones is the first iteration, and then the blue one is the correct. And it basically converges, and I just took 2 time slices here to show you this. And then you get, at the end, you get a nice reconstruction. Okay, some literature to close and give you time for lunch and photos. Inverse problems in Neurofield. We worked on this for several years, going step by step with the Amari equation and the inversion. And also, perhaps I can point out that the synergy of inverse problems and data assimilation techniques, there was an initial paper by Melina Freitag and myself some years ago. Neurofield theory, there's a Springer book on this. And in inverse modeling, we try to put data assimilation and inversion into some resonance. And here's a recent paper on the kernel reconstruction for delayed neurofields, and there are 2 papers to come, hopefully soon, on the convergence of these methods. Thank you very much.
Thank you, Roland.